This talk is by Dr. Luis Garza from Johns Hopkins, where he's an associate professor of dermatology.
Thanks for the intro. Okay, so for the next 10 minutes, I'm going to tell you guys about how we think double-stranded RNA connects WNTs and prostaglandins to control during wounding. So basically, first, a quick introduction to prostaglandin synthesis. Basically, like you heard probably earlier, first off, there's cyclooxygenase enzymes, which convert arachidonic acid to PGH2, and then that is metabolized by a group of different synthetases to individual prostaglandins, which each then have their own receptors, and all of these have different functions. So work that I've done within George Pastorellis' lab was where we were looking at male pattern hair loss, and we noticed there was this difference between prostaglandin D2 being elevated in the bald scalp and E2 being deficient. So that was one indication that prostaglandins are important, but there's many others, for example, like the work on the tanaprost and prostaglandin active alpha. Also, we know WNTs are clearly really important for hair follicle function. So, for example, in the work that Mayumi Ito did with George Pastorellis, they know that WNTs control the wound-induced keratinogenesis. And also, in particular, WNT7B is really known to regulate hair follicle cycling. So one question is, well, how are WNTs and prostaglandins related? One clue comes from some work that was done in zebrafish and published in Cell in 2009, which showed that prostaglandin, I should say prostaglandin E2, sorry, can actually, prostaglandin E2, the synthase, we're referring to the synthesis, but basically prostaglandin E2 can stimulate WNT to control heart regeneration. So generally then the idea is that these good prostaglandins like E2 and F2 alpha and WNTs might be pro-stem cell and enhance hair follicle cycling and certainly enhance hair follicle neogenesis. And then these might inhibit hair follicle neogenesis and regeneration and cause alopecia. But one question we wanted to ask is, how are the WNTs and prostaglandins related? And is there something that's upstream of both of them that might coordinate? So to do that, we looked again at this wonderful discovery that Mayumi and George had done, where after this really large full-thickness wound, at the very center there's regeneration of new hair follicles and a de novo organogenesis. And we wanted to try to ask what regulates that. So we did screening of mice that did it really well and mice that did it really poorly. And we found that double-stranded RNA correlated very well and even had functional ability to induce new hair follicles forming after a wound. So double-stranded RNA is thought to be released from a wound. We showed that it binds Toll-3, and then Toll-3 is necessary for hair follicle regeneration. So our hypothesis then was that double-stranded RNA might coordinate both prostaglandins and WNTs to enhance hair follicle neogenesis. So to do this study, I already introduced you to the WNT assay, where we do these large wounds in the back of mice, and then we do confocal microscopy to quantitate those new hair follicles forming in the center of the wound. And then we also cultured normal foreskin keratinocytes, treated them with a bunch of different things, and then would do PCR, Western blot, and immunohistochemistry. So that's the methods. So first off, just to show you what we found repeatedly is that if you inject just a single dose of even as little as 500 nanograms of double-stranded RNA, like a couple days after wounding, 2 weeks later you'll see dramatically higher amounts of regeneration. Coordinate with that, we also see there's increases of WNT7B expression after that double-stranded RNA injection. And when we treat human keratinocytes in vitro, we can find there's a really beautiful dose-dependent increase of WNT7B expression according to the amount of double-stranded RNA we're treating with. And we can also see that on Western blot. So then we were curious about looking in some of our knockout models. So if you look at a Toll-3 knockout mouse that has much less WNT7B present, and then now if we try to rescue it with a downstream signal, we think IL-6 is downstream for double-stranded RNA, we can rescue that WNT7B expression. Also, if we look at a STAT3 mutant mouse, we see decreased WNT7B. So indicating that the pathway is probably double-stranded RNA to Toll-3 to IL-6 to this WNT, this wound-induced keratinogenesis. And then we want to say, how is it working? So here we showed that it's through Toll-3. So if you knock down the Toll-3 receptor, you can decrease this WNT7B expression. So clearly, Toll-3 is required for WNT7B. So then we looked in vivo in mouse, now at the COX-2 side of the cyclooxygenase. So same thing here. If you take a mouse and you wound the mouse, you see dramatically increases in cyclooxygenase expression. And then we can show that that's happening through double-stranded RNA. So again, if you do a dose response curve, we see really beautiful increases of the cyclooxygenase 2, PGS2. And we also find nicely that it looks like the double-stranded RNA is inducing more of the prostaglandin E synthase and less of the D2 synthase. So then we tried to do rescue experiments, and first we did mRNA, and we were a little surprised. It didn't really show us what we thought we were going to see. So first up here is if you just do mock, and here, so we're not doing any knockdown, and we just add poly-IC, again we see this really nice increase of Win7b. And then now, if we knock down the COX-2, we can dramatically inhibit that. So just, again, showing that the Win7b increase really requires COX-2. But then we said, well, can we rescue it now? So we did that same knockdown where we added either a bunch of different prostaglandins. D2 just caused cell death, so that didn't work. But none of them actually increased the mRNA of Win7b. So we were a little bit concerned by that, but when we looked by protein, it made a lot more sense. So again, by protein, looking at Win7b, if we're just doing mock transfections and we add double-stranded RNA, we see a really nice increase of Win7b. If we knock down the cyclooxygenase, again, it's really dramatically inhibited. But now, in contrast to the mRNA, the protein is much more stable now with D2, so we can rescue it. And we even somewhat rescue it with F2 alpha, but again, we couldn't detect D2 because we just got a lot of cell death. And this is just showing the quantitation of multiple different Western blots, just showing that same pattern held over many experiments. So then we said, okay, well, let's start looking if we can do rescue in vivo. So the first thing we did is we treated, and with the double-stranded RNA, we saw large increases of wound-induced herniagenesis. If we add celecoxib, we can decrease that amount of herniagenesis. And then what we did is we did both the double-stranded RNA and the celecoxib, so it would be like this, but then we added the prostaglandin E2, and we could recover some of that expression. So basically, the conclusions are that Win7b expression in wounds correlates with wound-induced herniagenesis, that Win7b production is dependent on the COX-2 enzyme, and it can be enhanced by prostaglandin E2, probably your protein stability, since we saw it more in protein and less in mRNA. And then PGE2 rescues Win7b protein, as I mentioned, and then can also help induce Win. So the bottom line is that noncoding double-stranded RNA and toll-free signaling are coordinating prostaglandins and Wins. So they're basically both, it's kind of a really upstream regulator. And that was our main goal when we started these studies. We were really curious, what are the earliest events in wounding that reactivate some of these developmental pathways we've heard so much about in this conference? Like from when we heard about this beautiful role of sonic hedgehog and complementing her work that she'd done on Wins. And what we were really curious about at the start of this is what are some of those earliest events during wounding that reactivate these developmental programs? And it looks like it's double-stranded RNA. So a lot of this work was done by Amadeus Zoo. His parents named him that because they loved Mozart's work so much. And no joke. And these are the other folks in the lab who helped out a lot, and our collaborating labs and our funding organizations. Thank you.
Open for discussion.
Nice presentation. Just a very dumb question. Do you have any evidence that this beautiful new mechanism you unveiled actually happens in real human skin?
Yes. Yeah, we do. We actually have really good data on this that we haven't published yet. So we've done microarrays on people that have been treated with rejuvenation lasers. So, and we did this study probably cost like, we did it with a collaborating company. It probably cost us hundreds of thousands of dollars. We did 17 people. We did microarrays on everybody. We did microarrays before laser rejuvenation of the face, as well as periodic times afterwards. And we screened every single gene in the genome to see what correlates with photorejuvenation of the face. And the #1 pathway is double-stranded RNA.
Wow.
So it's clearly...
And also TNF3, the whole sequence?
Yes. It's the #1 pathway. Basically, it's an immune sensing pathway that activates these double-stranded RNA sensors. So yeah, we actually have very good evidence that it's a sequence. Yeah.
Right.
Sure.
Nice talk. Yeah. So I was curious, did you look at other Wnt ligands? Only Wnt7b is upregulated?
Yeah, when we did microarrays, we treated double-stranded RNA, and we did minus and plus, and we did microarrays, and Wnt7b was the highest Wnt ligand. And there were some Wnt ligands that were inhibited, and I'm forgetting what they were. 5A might have been one of them. But Wnt7b of those ligands just was the biggest. That's why we concentrate on Wnt7b.
Yeah, another question is that it's very interesting about your discovery of the dsRNA. Have you ever tried to apply the dsRNA in intact skin? What response can be seen?
Yeah. One thing we were curious about that some reviewers asked for the stem cell paper we had is they said, well, double-stranded RNA really potently induces Wnt. Does it induce antigen? So we took telogen skin and we added a dose of double-stranded RNA, and it did not turn on antigen. And now, through several years of work, what we understand is we did all of this work. Look, again, like I said at the end of my talk, trying to assess what are the earliest events in wounding that trigger some of these development pathways. So what we think double-stranded RNA does is at the beginning of, we treat it 2 days after wounding, and what we think it does is it maintains cells in a quiescent stem cell phenotype so they can crawl across and then be competent at the later stages where a lot of you guys are looking. And so we think that when we inject it in mice, we're not turning on antigen because we're actually preventing differentiation. So that's why it's maintaining cells in a more kind of telogen-like state. So we know that, but we haven't done exhaustive microarrays on healthy skin with double-stranded.
Thank you very much. Congratulations for great work.
Thanks for having me. Thanks for your inspiration.
Can you tell me, have you looked at the correlation between the size of the wound and the presence of the TLR3 pathway?
Yeah, that's a really good question. I know, because I was curious about that from my own recent work too, which I showed the small ones didn't have it. We do know that there is a relationship between damage and release of double-stranded RNA. And so it looks like there probably would be, but we haven't ourselves quantitated that carefully. So we have kind of anecdotal sense of that, but we haven't. That's something we should.
Yeah, you can imagine in a human situation where you're microneedling that this might be very interesting thing to.
Yeah, definitely. I mean, the general point we like to make is if you think about what dermatologists love to do, they torture their patients. They dermabrate them, they put needles on them, they laser them, they peel them. All of this stuff is for facial rejuvenation, and the only thing it has in common is damage. So we think it's all really happening in this double-stranded RNA.
Really interesting talk. So, just to follow up on the previous question, is there a critical window of when you can apply double-stranded RNA to a wound and a time when it's no longer effective?
Yeah, we definitely know that if you do it too much, so what we've done recently is we've not done it just 2 days after wounding, where we, again, do like 500 nanograms single dose. We tried doing it a lot, and it actually inhibited regeneration. If you just continuously give the double-stranded RNA, again, we think it's because cells are being maintained in this quiescent state, and then they can't differentiate. So, yeah, too much is bad, and we think that might be actually part of, might explain some human scarring.
Okay, thanks very much.